Pegambarian endowed chair. He's a professor here at Optical Sciences. He received his BS at the Indian Institute of Technology. His PhD is from MIT in electrical engineering, EDCS. He was at Raytheon for a good part of his career, where he was the lead scientist of the Quantum Information Processing Group. Many awards. You guys have seen his bio on that. I would encourage you to read Professor Guha's bio. And with that,
thank you so much, Ron. All right, pleasure to be here. Lots of familiar faces. Feel free to interrupt me as I speak. I will give you a brief flavor of work we have been doing as part of an ERC called the Center for Quantum Networks. It's an engineering research center that many of us here in this room are part of. I'm with the College of Optical Sciences. Have joint appointments with the ECE department. So I'll tell you a story about something that doesn't exist. The quantum internet. I mean, we have heard a lot about that. We all think differently about what it might be. We have different visions about it. So I'll tell you what at least my vision is, or how I like to think about it. And I'm sure none of us will be proven right in one way or the other. Think of imagining what the internet is like today back in the 60s when people were working on the ARPANET program. So we are kind of at that point with regards to this big initiative. So with that, let me take you back to to a picture of the first digital computer called the ENIAC. I'm sure a lot of you have heard about it. 1945. This was the first time that a machine could do a computation using bits by manipulating collections of bits that were encoded in vacuum tubes. A computer that occupied a room about this size, to do computations that were not possible by other means. So that was a big step in the history of computations. I mentioned the ARPANET program, but there was a succession of projects that started with the ARPANET, eventually leading to NSF-net, the CS-net, and a succession of programs that basically brought that bit outside of that box and connected multiple computers, transmitting packets of bits from one point to another. The company I worked at, BBN Technologies, which was acquired by Raytheon in 2009, the year after I joined, they led this program. And I still remember I had a pleasure of meeting and working with lots of people who were involved in this program, and they could not imagine what the internet would be like today and what would it be used for. So this picture is a picture of a quantum computer. A lot of you in this room have heard about it and are working on it. This is a quantum computer that Google wrote a paper on in 2019, and it works with qubits. So qubit is a quantum extension of the concept of a bit, a binary digit, something that can live in a superposition of the states of 0 and 1. And if you want to think of mathematically, 0 and 1 are two unit vectors and a qubit can stay in any superposition of those two. And the fact that a qubit can be in superposition of one of two states, it means that n qubits can stay in a superposition of any 2 to the n possible states. So when you do computations with qubits, you can do gates and actions on say n qubits. So you can act on all of those a superposition of 2 to the n states at the same time. And because of this, what happens is that although when you at the very end, when you make a measurement on these qubits, only one of those 2 to the n possible outcomes show up, you can arrange computations with qubits to be done in a way that there are certain problems that quantum computers can solve that classical computers cannot. And there are examples of that you know of, like factoring is one example. This particular computer, they solved a problem that was not that useful. They solved a useless problem, but that useless problem they solved in a few minutes, which the world's most powerful supercomputer will take months, if not more, to solve. Well, I'm saying it's a useless problem, but it's a problem that falls under the class of what are called sampling problems. It generated random samples from a probability distribution, that is hard to sample from. You must have seen these Dalton boards in science museums. They drop a ball and it rattles around these little nails, and then you over time you see this probability distribution, the Gaussian curve emerge. So every time you're dropping a ball, you're generating a random sample from what is called the binomial distribution. And it's a distribution that is easy to sample from. But then this computer generated random samples from a distribution that is hard to sample from. You cannot write a classical computer code. Anyhow, so this was a picture of that paper that Google published, quantum supremacy. This is the phrase that people have been using. Not a big fan of this phrase, but this has been around. Quantum supremacy is supposed to mean you can to be able to do something with a quantum machine that you cannot do otherwise. When two qubits are in a state that cannot be written as a product, as a description of the state of the first qubit and the description of the state of the second qubit, when they don't factor, you say that those two qubits are in an entangled state. Most states of multiple qubits are entangled states. The Center for Quantum Networks is an ERC, it's an engineering research center, which it's a 10-year-long center. We are right at the end of the second year. And we want to sort of try to retrace the history of the ARPANET program, along with not just us, but many others across the country and across the globe, to try to connect quantum computers, take that qubit outside of that box and transmit qubits over long distances, over short distances to long distances. But qubits are much more fragile than compared to bits, so transporting them requires a lot more care. You have to still encode qubits in photons to transmit them over optical fiber, but you have to do more things in order to make sure that that transmission is faithful. And hopefully this endeavor is going to lead us to a quantum version of the internet that connects quantum powered computers, sensors, and different gadgets over long distances. I was thinking yesterday, wouldn't it be such an opportune time for this talk? Obviously none of this was planned, but you all have heard about the Nobel Prize in Physics that was announced a couple of days back. These three gentlemen, they were credited with some of the earliest work that led to the understanding and establishment of what entanglement really is. John Clauser, his name is attached to something called the CH-SH inequality. Clauser, Horn, Shimon, Holt, and it's an inequality that even today when experimentalists create entanglement in the lab, one of the first things they do is to test that CH-SH inequality to ensure that what they have is actually non-local correlations, an entanglement that cannot be described by any classical probabilistic correlation. Anton Zeilinger, he demonstrated entanglement over a distance. He used it to teleport qubits. He also, I believe for the first time, converted entangled states into shared secret whose security promises lies in the laws of physics, as opposed to our belief that certain math problems are hard to solve. Alain Aspect, when he improved the notion of non-locality and came up with a Bell inequality violation test. So the Aspect's Bell inequality violation test and the CH-SH inequality are some of the earliest notions of how do you quantify something that is entangled. So I mentioned a qubit can be in a superposition of a 0 and a 1. One of the things about a qubit is that when you measure it, you see it in one of those two states. If you measure it in the basis 0-1 basis, it collapses to either the 0 state or the 1 state. You don't get to see the superposition. Now, you could decide to make a measurement of the qubit in a rotated basis. Like I'm writing that plus and the minus are two orthogonal states that are superpositions to 0 and the 1, but they're still at 90 degrees. So I can choose to make a measurement in that rotated basis. But when I do so, my answer will be one of these two states, the plus or the minus, but this time the qubit is going to collapse to the plus or the minus state probabilistically again, except that the probabilities now will be magnitude squared of gamma and magnitude squared of delta. So depending upon which basis you're measuring on, the probabilities of the outcomes can change. Now, if I take this particular entangled state that I wrote down, this is actually this is called the Bell state, named after John Bell. So this state actually is still one of the most profound entangled. This is a maximally entangled 2-qubit state. This state cannot be written as a product of the first qubit A and second qubit B. Now, if you just do a little bit of math, it's easy to see. If you express 0 and 1 in this plus-minus basis, it looks like this. It looks like plus, 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 minus, minus. And it looks like a very simple thing, but the fact that the Bell state can be written like so in these two bases, this was the underlying reason why the Eckert 91 protocol for turning entanglement into a shared secret that whose security lies in the laws of physics emerges from. So what do I mean by that? Well, let's say Alice and Bob share many copies of this entangled state. And both of them decide randomly to make a measurement on their qubits in either the 0-1 basis or the plus-minus basis, completely randomly. They don't need to coordinate. And after they're done making those measurements, they can compare their choices of the measurement bases over a telephone line that somebody else could tap. And they can take a record of what are the instances where they happen to choose the same basis. And in those instances, no matter which basis they would have chosen, they would have gotten the exact same answer. If they chose both the 0-1 basis, they would have both gotten 0 or both gotten 1. But if they both chose the plus-minus basis, they would have both gotten plus or both gotten minus. Okay, so, of course, you cannot generate and distribute this perfect Bell state to Alice and Bob. But turns out, and I'm going to spare you the math details, that even if you have imperfect Bell states, noisy entangled states shared between Alice and Bob, they can make measurements at their end in randomly chosen basis and follow that by a suite of steps called error correction, privacy amplification, to turn that into a shared secret bit string that nobody else in the world has any access to. So, and this, of course, can be then used to do secure communications by one-time pad. So this is one of the earliest applications of quantum communications that still is quoted as one of probably the first one that people will see implemented. But there are many other applications of entanglement. The fact that entanglement can be turned into shared secret is only one of the applications. The other thing about quantum mechanics or quantum information is that you cannot make a copy of a qubit. I mean, we make copies of bits all the time. We just did. Copied that file from my computer to Julie's computer. Doesn't work for qubits. You cannot make copies. And why so? Well, you can see if I were to be able to make a copy of that qubit, millions of copies, I could make measurements on all of them in different basis choices and learn the value of alpha and beta. But I just told you that you're not allowed to learn the state of the qubit. You get to measure it, and it will collapse to either the 0 or the 1 state. You only get to see the measurement result. You can't copy it, so well, you might ask, how would you send a qubit from point A to point B? So that's where the fun word teleportation comes in. And it's not as fun as Star Trek, but it is a very curious concept that you can take a qubit, alpha 0 plus beta 1, that Alice is presented with, but she and Bob share one of these Bell states. Okay, so what Alice does on her end is that she makes a measurement on her two qubits, but she doesn't measure them each individually. Quantum mechanics tells you that a measurement has to be described by a set of orthonormal vectors that span the Hilbert space in which your state belongs. So for 2 qubits, I can write down these 4 states, take that first Bell state, but write 3 other states, such that all of these 4 states are 4 mutually orthogonal vectors in the 2-qubit Hilbert space, 2-qubit vector space. So I can do a measurement in that basis. Now, how do I do that measurement physically? That's a different story. You can use, for example, in linear optical qubits, you can use a beam splitter to do that measurement. If you were to do the Bell basis measurement on these 2 qubits, you would get one of 4 answers, right? You will get a 2-bit answer. So Alice transmits that 2-bit answer to Bob, and turns out that depending upon which of these answers Alice gets here, the state of Bob's qubit, is projected onto one of 4 states, which Bob can apply a local unitary operation on, a local rotation on his qubit to retrieve the state of the qubit that Alice had. So Alice never read her qubit, but she was still able to teleport it, send it to Bob, but she consumed this 1 e-bit, 1 entangled bit worth of entanglement. So this is called teleportation. Now the Bell basis measurement can also be used to connect 2 entangled states generated over 2 distance fragments. So A to B is a Bell state, C to D is another Bell state. And let's say I'm sitting here, I control both qubits B and C. I could make a Bell measurement on the qubits B and C. And depending upon which of the 4 answers I'll get, my A and D qubits will be projected onto one of these 4 Bell states. And again, if you choose to send that answer to one of the two sides, you can make a local unitary correction to turn the AD state into one of the generic Bell states that you desire. So this method of turning entangled states over small fragments by doing local measurements into entangled states over larger fragments is one of the basic tenets of how entanglement distribution over a network works. And there's obviously a lot more details to that. I'll get to some of that. So let's take a little break and discuss why should we care about this. So I mentioned QKD as one example. One of the other important applications of a network that is often quoted, and a lot of people working on this in the community, is cloud computing. Quantum computers are expensive, and they are still not there yet. But quantum computers are at a point where 50 to 100 qubits can do things that a classical computer cannot, even though they are so far they are doing useless things, but they can do things that are not doing possible classically. When they become useful, then if you want to access a quantum computer to run your own proprietary algorithm on it, and you don't own a quantum computer, you will be wanting to run it over the cloud. So one possibility is that you send the instruction to IBM or Google, whoever has the quantum computer, on an email or on some secure line, and they can do it for you and send you the result of the computation. But then they also learn what you just computed. What if you wanted to do quantum computation on a computer on the cloud, but with a provable guarantee that they will not find out the algorithm that you ran on their machine? And the only way to do that, or manage to do that, is if you are quantum connected to that quantum computer. If you were able to transmit qubits reliably between your station and to IBM or Google, whoever owns that quantum computer. So that's an important application of a quantum network. A few students in my group, they are looking at using distributed entanglement to enhance networks of sensors. I mentioned teleportation. So teleportation can let you teleport a state of a photon, state of a qubit from one point to another. So imagine if you had long baseline astronomy. We all saw that picture of the black hole from the long baseline radio astronomy that University of Arizona was part of, a big part of a couple of years back now. Optical frequency long baseline telescopes, if you have different telescopes that are not co-located at different places, if you were able to magically bring all the photons collected from all these telescopes into one volume of space losslessly, perfectly, and you do an interferometric measurement on them, you could create an effective baseline, an effective area of the telescope that spans the whole area where the telescopes belong. Roughly speaking, there are more details to that. And as you know, the size of the telescope determines the resolution, how small of a thing you can resolve. So since by teleportation you can send the state of a photon from one place to another, it should be immediately obvious as to why, if the two telescope locations or the multiple telescope locations were to be able to share entanglement, then they won't need to send those photons. They will just take the photons from the starlight, load them into their local quantum memory banks, and use the distributed shared entanglement to effectively do the exact same long baseline telescopy, which is right now only in the realms of science fiction, possible with distributed entanglement. Now, what happens when such an entangled state is distributed by a network that is noisy and probabilistic, and you have to do entanglement distillation? How do you load those photons into the memory banks? There's lots of interesting open problems in that space. Entanglement can also help locally. You don't have to go to a long, big network. We have a few students, faculty in the group, looking at various types of quantum enhancements in photonic sensors. So one example picture here, this is actually work we are in collaboration with Del Wilson over here. Atomic force microscopes. You scan a nano cantilever over a surface, and you shine a laser light off of that. And small longitudinal displacements of that cantilever turns into a lateral displacement of the beam that you can detect with a camera. Okay. Now, if you look at the full space bandwidth product of that propagation geometry, you can ask yourself, what if I generated an entangled state among co-propagating orthogonal spatial modes of that beam that is interrogating that cantilever? And turns out that using entanglement here can give you, in this case, maybe between factor of 10 to 100 improvement in the resolution with which you can assess that displacement. So in this case, it is an entangled sensor network, but those individual sensors are nothing but these co-propagating spatial modes. Secure communications is only one application I talked about of turning entanglement into shared keys, but there's a whole suite of work that people in the community are working on various types of distributed computations that underlie logistics, decision making, secure function computations, auctions, symmetric private information retrieval. So you're trying to query a database with a guarantee that they cannot know what you looked up, while they have a guarantee that you did not access anything more than you paid for. So all of these problems, there are classical cryptographic solutions, just like there is a classical cryptographic solutions to key exchange called Diffie-Hellman. But most of those classical cryptographic primitives that solve these problems, they are not quantum secure, meaning their security is not immune to a quantum computing attack, which is why quantum information processing gives you these way to solve these problems that are quantum secure. One fun thing about quantum computing I wanted to mention is, so we all have seen the usual kind of quantum computing where you have a set of qubits that you prepare, they go through a set of gates, and then as the qubits go through the gates, they get entangled in some superposition of all possible, say, 2 to the n possible states, and you then make a measurement. And the act of the measurement collapses the state of the qubit to only one of those 2 to the n states, which hopefully carries the answer to your problem. That's how all quantum algorithms look like. Peter Shor's algorithm that can factor numbers efficiently, Grover's search algorithm, all of them look like this. This is called the circuit model of quantum computation. This is how IBM, Rigetti, Google, all of their quantum computers are built this way. There is an alternative way to build a quantum computer. It's called the cluster state model of quantum computing, or measurement-based quantum computing. Here I'm showing a control Z gate. Okay, so control Z gate is you take 2 plus states. 2 plus states, if you write the whole state, plus, remember, is 0 plus 1 over root 2. So if I expand the product of these two, I'll get something like this, except that I'll have a plus sign here. So control Z gate here, it flips the sign of the 1 state if there's a 1 here. So only this state gets a minus sign, and that's an entangled state. This particular kind of entangled state is called a cluster state. Now I can take many qubits and put them on a square lattice. I place those qubits, each one of them in a plus state. And wherever there is an edge, I do a control Z gate. And I create a cluster state in this graph topology. And it turns out that there is a way in which I can map any computation in the circuit model into the cluster model, where instead of passing a set of qubits through a set of gates, you prepare this generic entangled state called the cluster state, and you simply make single qubit measurements column by column by column. You just make one qubit measure it off at a time. But every measurement that you are doing, you will choose the measurement basis adaptively based on the previous measurement result you got. And one can show that at the end, the last column of unmeasured qubits will be in the exact same state that you would have gotten at the end of that quantum circuit before you made the measurement. So obviously, if you measure those off, you will get the answer to your computation. So it's a very interesting model of quantum computing, but it's particularly good for photonic quantum computing. So because photons like to fly, they don't like to sit in one spot. So you can weave the cluster from one end and keep measuring them up from the other end. Now, one thing about the cluster state model of quantum computing is that we don't know what is the most resource efficient way to embed the circuit into the cluster model. Meaning, if I give you a quantum circuit and ask you how big a cluster state, how many qubits do I need in order to map the circuit into the cluster? So this is funded on the CQN's Education Workforce Development Fellowship Program. Student Ashlesha Patel, she came up with a computer game. Have you played the game of Tetris? It's a tangram puzzle. It's a tiling puzzle. Okay, you have these little pieces, different shapes falling from the sky, and you have to rotate them and then put them in. So Ashlesha came up with a version of the Tetris game, but different set of rules. You can explain her rules to a high school student. So you don't need any quantum. But she shows that if you play her game and get better and better at it, you will find progressively more and more resource efficient ways of mapping any quantum circuit into the cluster state model of quantum computing, which is a known hard problem. So anyway, so there's an undergraduate student, Josef Jacobson, who is helping Ashlesha write the code for that. So let's go back to talking about communications. I talked about applications for a little bit. Ron, how long do I have? About 30 minutes. Thank you. So this is a cartoon of the quantum internet that we drew for our ERC proposal. It shows quantum data centers, quantum computers, and maybe even handheld gadgets that are connected to the quantum internet, that are all connected by an infrastructure that can faithfully transmit qubits from one point to another. In the future, just like on the internet, there are many applications running in parallel. There is Zoom, there's email, there's WhatsApp, there's everything. The internet is supporting billions of applications simultaneously. Similarly, there'll be an Eckert 91 session for key exchange, a distributed entanglement-based telescopes. There'll be, entanglement, where there's assisted symmetric private information retrieval. All sorts of applications will be happening together on the quantum internet. So you have to design the internet to be able to cater to all these applications at the same time for the desired accuracy, desired fidelity, desired kind, desired quality of entangled states that they need. One of the things that a quantum network will require us to build are things called quantum repeaters. So if you know, in classical communications, you have to detect, regenerate, and repeat a classical signal because they deteriorate in quality as in propagation. Quantum repeaters, unfortunately, are not as easy as optical amplifiers. So you have to build, they are small, special-purpose quantum computers that you need to clean up the quantum signal. So that's a big focus of the center. Before I tell you more about quantum communications, let's talk a little bit about classical communications, because I realize this is a crowd that mixed backgrounds, but if you have seen any book on digital communications, you would see there's a set of steps that you go through to communicate information from point A to point B. When you're talking on the phone, you generate an analog signal, like your voice signal. And that voice signal gets transduced into some form of an electrical signal, like a voltage or a current. And typically the next step that happens is that you sample that signal. You sample it periodically. Why do you, and how often do you sample? Well, that is determined by what's the bandwidth over which your relevant information is there, and use the Nyquist criteria to generate samples. But each sample is an analog value. So what you do is that then you quantize. You take each analog value and digitize that into a set of, in this case, I'm showing 4 bits. So each of those samples I'm writing as 4 bits. So that number of 4 obviously is arbitrary. And in some cases, the information might already be digitized. Well, you don't send that quite yet on the channel. So this is still inside your phone. You have digitized your voice. At that point, what you do is that you do error correction. So you take each of those 4 bits, and in this case, I'm showing you take, say each one of those and then expanding them into a longer stream of bits. So that error correction code that I'm showing here is taking 3 bits at a time and encoding them into 6 bits. So you're adding redundancy to the bit stream. And that's when you are ready to send the signal over the channel. So you modulate it. So modulation means that every time you see a 1, you send a particular state of a laser pulse. If it's a 0, you send a different laser pulse. So what I'm showing here is a binary phase shifting modulation. Laser pulses with the same mean photon number, but with 0 or pi phase. That's what is sent on the channel. That goes through some noise, loss, dispersion. This is your propagation. And after the propagation, you get your noisy version of that optical modulated code word. That is what arrives at your receiver. And then what you do is that, well, you receive it with a receiver. And the receiver typically has 3 segments of it. There might be some optical pre-processing that you may need to do to that signal. And then there's a detector. This detector's job is to convert the optical signal into electronic signal. That's where light goes from photon to electron. And then you have some electronic signal processing, and that produces your guess of these encoded bits that you send. But see that some of the bits are in error. The blue ones, they flipped because of error in the channel. But that is where error correction code's power comes in, and the decoder acts on those, and hopefully, if your overhead that you added in the error correction code was commensurate with the noise in the channel, you retrieve your data that you had sent at the inputs, your digitized data. And then you go through the reverse of every step. You interpolate, you filter, you transduce, and you get back your analog signal. And that's what happens when you're talking on the phone or Zoom. So all of this is under, and of course there is a big part that I did not get into, is that there's a lot happening over here in that noisy propagation that I'll not go into right now. So before I talk about sending qubits over the channel, which is the subject of the ERC, let's continue with this thought of classical communications. I'm sending bits of information encoding in laser light pulses. Light is quantum. even laser light is a quantum mechanical object. The quantum description of laser light is called a coherent state. So you can ask the question, if I give you these 8 laser light modulated BPSK code words, what receiver will minimize the probability of error of choosing between them? The way I would, if you're familiar with binary phase shifting modulation, you guess like what receiver would you use it, the one that we have in the lab right now? If I give you one of 2 laser light pulses with 0 or pi phase, what would be the most obvious way to detect it, to tell apart which one is it? If you put it on a photodiode, it's going to give you the same click pattern because they both have the same energy. Can somebody suggest what receiver would you use if you had a binary phase shifting modulation? Sorry? Coherent receivers, exactly. Coherent receivers, thank you. So coherent receivers, you would beat the signal with a local oscillator and then do a difference amplification. A kind of coherent detection I would use for this is homodyne detection. So if I use homodyne detection or any form of detection that is detecting each one of these pulses one at a time, followed by any form of electronic domain post-processing, including any soft information processing, my error probability of telling apart between these 8 code words will be limited by this blue line. Whereas something called the UN Kennedy and Lax theorem from 1975 evaluated on those 8 quantum states, pure states of light, it tells us that there must exist a receiver that can tell apart between these 8 code words with a probability of error that is about 2 orders of magnitude lower. Doesn't tell us how to design the receiver, but that is the subject matter of this paper that Narayan Rangaswamy, who was a postdoc with Banevasic, is now just joined the ECE department as faculty. Welcome to read that paper. But essentially, that receiver is a small quantum gadget. It's a small quantum computer. So even though your light is classical, even though you have a tensor product of coherent states, quantum information processing can play a role in better extraction of information. You can then ask the question that, well, what is the capacity? How many bits you can send per transmitted optical pulse if each of the pulses that are arriving at you have a mean photon number of n, where ns is the transmitted mean photon number per pulse and eta is the transmissivity of your channel. There is something called the Holevo capacity that gives you the maximum capacity that is allowable by any receiver, including ones that make collective measurements on the long code word blocks. And if you plot this slightly differently, if you take the bits transmitted per pulse or per temporal mode, the x-axis, this is how fast you send information, or it's called spectral efficiency. Plot it as a function of photon information efficiency, or bits per photon. There is a trade-off between these two. You cannot do both. If you want to be more efficient with respect to your photon in terms of encoding, you must send your information slower versus vice versa. The black line is the Holevo limit, and all the different colored lines are the Shannon information theoretic limits associated with the best possible design of those receivers. So there is a fundamental gap that is there to close, for which you need quantum receivers. And if you want to go beyond that, you need classical repeaters or optical amplifiers and signal regeneration. So I talked about classical communications and the fact that you can benefit from having quantum processing at the receiver. What if you are in a scenario where you are still sending classical data, but you are working with the advantage that you have ancillary shared entanglement to assist with improving your classical data communications? In this scenario, if you are in a regime of high thermal background noise, so NB is the mean thermal photon number that the channel adds per transmitted mode, NS is the mean transmitted signal photons per mode. When NS is small and NB is high, there can be a significant improvement you can get in your classical communications capacity over and above the Holevo capacity, over and above the best possible rate that you can achieve without any shared entanglement. So for classical communications already, quantum receivers can help and entanglement can help in this particular scenario when you're in a low photon number regime. And this realization of low transmitter brightness and long center wavelength to hide your information, this also resulted in my colleague Bulat Bash and Christos Gagatsos, and they looked at applying this idea for covert communications or undetectable communications. So meaning your communication attempt is undiscoverable by a quantum powerful adversary. I'll let you read those papers, and if you have any questions, I'm happy to answer. Let's go back to the point of the the whole communication train when you are now sending qubits. So far I've been talking about sending classical bits. If you send quantum information, there is still the quantum version of the analog signal which I cannot draw anymore. I cannot draw the field. The field becomes an operator. You have to talk about the wave function and talk about probability distributions for various dynamical observables. But you could still digitize any quantum information into a set of qubits. Those qubits in general will be entangled. But after that, you have to follow almost the exact same set of steps. You have to error correction, modulation, and then receiver. And when you are sending qubits over long distance, there is really no other kind of bearer of quantum information other than optical frequency photons. You cannot send qubits using electrons over long distance unless you cool down your optical fibers to hundreds of millikelvins or lower, which is obviously impractical. But optical photons are the bearers of your information. But remember I talked about teleportation. So there are fundamentally two different ways in which you can send packets of qubits faithfully. One way is to just mimic what we did with classical communications. You take k qubits, you encode them into n qubits, n is larger than k, you send them over a noisy channel, you retrieve the noisy n qubits at the receiver, you put it through a decoder, you retrieve your k qubits back. Okay, so this is forward error correction, or one way. But instead, I could do a different way of quantum communication. Now, I take those k data qubits, but I hold on to them. What I first do is that I generate n noisy bell pairs, and I put them through a decoder on both sides to distill down to k good quality bell pairs, and use those k good quality bell pairs to one by one teleport those k data qubits that I have been presented with. So this second form of doing quantum communications is called two-way quantum communication, and most of our quantum repeater work in CQN adheres to the second way, although the first way has some inherent advantages but requires more complex hardware compared to what we have right now. Professor Banevasic and Narayanan, they are looking at this job of entanglement distillation. The reason I use the same k and n in both cases is not a coincidence. Any error correction code for one way can be mapped into an entanglement distillation code for two-way. So entanglement distillation, you take n noisy bell states, say rho AB is the density operator of those two qubit states. You can put both of all the n qubits on Alice's side and all the n qubits on Bob's sides through a quantum circuit, and you measure off n minus k of the qubits after this operation. This is the error correction decoder or the distillation entanglement distillation code, and you retrieve k good quality bell pairs at the end. So you may ask, what is k over n? How many good bell pairs can I distill per noisy bell state? And there is an answer to that, and that is given by something called the hashing bound. But how do you develop codes that achieve this hashing bound, that comes close to this best possible efficiency which you can distill, or you can extract good quality bell pairs from these noisy bell states? And this is by itself a subject matter of investigation that we have done some work on, and extended this to multipartite entanglement is work that Narayanan is looking at as part of the center. Bane's group is collaborating with Liang Jiang at University of Chicago to develop one-way error correction codes as well, and this is a student Nitin who is leading that work, and I will not go into the details of that. With that, let me go back to the notion of capacity, so that I have talked about quantum communication, how it will work at the high level. There's one way or two-way, two different ways you can do it. What is the best rate at which you can send qubits over a lossy channel? So unlike classical communications, your data communication rate, your qubits you can transmit per transmitted optical mode, is fundamentally limited by the loss in the channel. There is no way you can crank up your power to increase the capacity. And that rate is given by this formula in qubits transmitted per optical mode, which roughly becomes proportional to the transmissivity of your channel when the transmissivity is very low. So when in the high loss regime, an optical fiber, eta goes as exponentially with the length of the fiber, your rate is limited by that exponential decay in the length of the fiber. Now, note that I'm writing these three tasks. When people say quantum communication, they're referring to one of those three tasks. Okay, and they're all interchangeable in the sense that task 1 of transmitting qubits and task 2 of generating bell pairs, they are equivalent. Why? Because I just mentioned that if you have a bell pair, you can use it to teleport a qubit. And if you have a service that can transmit a qubit using error correction, you can generate local bell states and send one half of them through the channel. So both of those two are interchangeable. And I also said how you can turn entanglement into shared secret. So task 3 of generating shared secret is also, all of these three tasks are limited by this rate, except that the unit changes on the y-axis. These twos here in the notation there denotes the fact that you are allowing for unlimited two-way classical communications as an ancillary resource. So how do you beat this exponential rate versus distance? There is no way we can build a quantum internet with this kind of a scaling. You need to insert something along the length of the fiber, and those are called quantum repeaters. Okay, so to build quantum repeaters, we need quantum memories. So let me take a little pause here and talk about quantum memories. So I'm going to talk a little bit now. This is all electrical engineering communication theory. I'm going to go into a little bit more physics, and then I'll connect it back to how quantum repeaters work and their performance evaluation. So the kind of quantum memory that our team is working with are atomic defects in diamond lattice. So the particular one we are working with, this was developed by my colleague, Professor Dirk England at MIT, and Misha Lukin at Harvard University. So what you are seeing there is a diamond lattice, and it's a tetrahedral lattice of carbon atoms. And a solid-state defect in diamond is where you have two nearby carbon atoms missing, and those are replaced by a silicon atom. If you work out the chemistry, there's a free electron of that silicon atom, and that free electron's ground state is what we use for your qubit. So they turn on an external magnetic field that, through a Zeeman effect, it splits the ground state into two levels. And these two levels, the up and the down that I'm showing here, those are your qubit. Now the upper arm, the first excited state, also obviously gets split, the down prime and the up prime. And the gap between the down and the down prime is roughly 737 nanometers. So that's an optical visible wavelength light. So what we do is that you start with, you initialize the qubit in an equal superposition of the down and the up state. And the way you do that is through a microwave transition. It's about a few gigahertz microwave transition. So you can do any single qubit gate. You can rotate that single qubit any way you want. And Matt Eichenfeld is our new faculty member here. He is looking at that problem of single qubit control. It's an extremely hard problem. How do you do single qubit gates on individual qubits precisely? But let's say you're able to do that. Then after that, what you do is that you turn on a laser at 737 nanometer. The down transitions, this population goes up to down prime, but this up doesn't go to up prime because this transition is not 737. It's slightly detuned away from 737. So what you generate, after that, if you turn off the laser pulse, the down prime emits a single photon and comes back to down. And that spontaneous emission process, it's a similar to emission. So this one photon comes down. It only happens if you started out with the down state. So you get an entangled state between the spin and that presence or absence of a photon. Now, what you can do is that you can initialize this this state in an unequal superposition of up and down, and you would get something like this. Now, what I could do is that we could turn this, after you turn on this laser pulse and turn it off, you can apply a microwave pi pulse to flip the qubit. Take the down to up and the up to down. And these two are two subsequent time bins. And then you turn on the laser pulse again and turn it off. And what will happen this time? Well, now the down state of the spin is going to emit a photon here in the second time bin. So the state of the spin, first time bin, second time bin, spin, first time bin, second time bin. So what you have generated is a state of a Bell state between the spin and what is called the dual rail encoded qubit in the photonic domain. A dual rail qubit is a state of a qubit encoded by the presence of a photon in one of two orthogonal modes, in this case one of two time bins. Okay, so this is how you can use the memory in an emission mode. You can use a quantum memory to emit a photonic qubit entangled with the state of the memory. Now, you can do the opposite. If you have a state of a photonic qubit in the dual rail basis, you can generate the spin in a first superposition of the up and the down. And this is a scheme proposed by Duan and Kimball years ago, Jeff Kimball's 2004. Through this interaction, through this cavity, what you can do is that you can have a conditional phase appear in over here for the case when the photonic qubit is in the state 1, 0 and the spin state is down. And the way you achieve that is that you turn the time bin encoded state into a polarization encoded state and only send the H polarized beam to reflect off of that mirror. And then after that, you apply a beam splitter to do a Hadamard gate on the photonic qubit, and you make a measurement with two photon detectors. at the end of the process, what you can show is that the spin state will be projected onto this state depending upon which of the two detectors you got a click on. And since you know where you got the click, you can apply another phase to the qubit in principle to get rid of that minus sign. So you can load the state of a photonic qubit in the state of the memory. So you can generate a photonic qubit entangled with the memory. You can in principle load the state of the photonic qubit into a memory. In this absorption mode of a quantum memory, Misha Lukin and Dirk England's group and Marco Lonca's group, they came up with a very interesting idea of doing a Bell state measurement among two photonic qubits encoded in the time bin, dual rail basis, asynchronously, meaning being able to take a photonic qubit that arrived at a node at a given time and another photonic qubit that arrived at here at a different time and be able to do a Bell measurement on it. They first loaded one into the memory, the other one onto the memory, and then did a Bell measurement. This is the most important primitive to build a quantum repeater. And they published this paper in 2020 where they beat the repeaterless bound, that bound that I showed a few slides back for the first time using a quantum memory. So this was right at the beginning of CQN. We were just proposing the center at the time where this experiment came out. Now, you generate an entangled, so now what you can do is that once you can generate a spin photon entangled state, you can do it in two different locations and have the photons entangled with the two spins. They fly on an optical fiber and meet on the middle on a beam splitter and do that photonic domain Bell measurement. And if that succeeds, you generate spin-spin entanglement. You can generate entanglement between two quantum memories at a distance. So this is one way you can create an elementary link of a spin-spin entangled state. The other way to generate an elementary link is to have a photon-photon entanglement source in the middle and send the photons out to the two sides and load them onto the quantum memories with the method that I just described. Now, you might ask which one is better. I don't know, depending upon, there's lots of architectural considerations depending upon which way you want to generate that elementary link of just one, hopefully good enough quality spin-spin entangled state, which you can then do entanglement distillation on and propagate further. So my student Prajit, he has done a comparison of these two encodings of photons in the single versus dual rail, and there is an interesting trade-off that appears that at a low loss, it turns out that dual rail encoding of the photon does better than the single rail encoding, even though eventually for high loss it scales poorly compared to the single rail scheme. So for example, if you're generating spin-spin entanglement for a local quantum processor, like a spin-based quantum computer, you might want to use the dual rail encoding scheme. And there is intuition behind why there's a crossover, which I'll leave it to if you have any questions about that. Prajit also looked at, along with Dirk England's student Kevin Chen, a design for a heralded multiplex high-rate photon-photon entanglement source for the second kind of entanglement generation that I talked about, where you have a photon-photon entanglement source in the middle and memories on the two sides. And we developed this with a satellite-based entanglement distribution in mind. And one of the things that we very quickly realized is that, well, even if we can build quantum repeaters with our memories in the next 10, 15 years or so, it'll be very hard to deploy them under the ocean. We'll have to have long-distance connections that are assisted by satellites. So currently, there is a program being envisioned by NASA in collaboration with NSF and the Department of Energy to potentially launch a medium Earth orbit satellite that can do entanglement distribution across the country on our two test beds. This is still work in progress, and it will be a very, very difficult program, but some architecture evaluations of that is going on. So let's say that we have that elementary link, entangled state of two spins across a length of optical fiber. And let's say you are able to do that over small segments of optical fiber, say this spin-spin entanglement here, spin-spin entanglement here, and so on. And you do that over many time bits, for example, or many frequency channels. And if I'm sitting here at this node, at every time step, I get the information about which of these links was successful. This is a probabilistics. The probability of a success for one of these spin-spin entangled states to happen will be proportional to the transmissivity of this segment. So if the segment's transmissivity will be eta to the 1 over n, if eta is the overall transmissivity, n is the number of segments, that's the transmissivity of each segment. So the probability that there will be at least one success is given by this formula, and if all n segments have at least one successful entangled state, and if all the Bell measurements in these repeater nodes succeed, n minus one of them, then you will get one entangled pair between Alice and Bob. And if you do the math, you can show that with this scheme, you can get a rate that outperforms what you can do if you give all the bandwidth resources and with the same temporal repetition rate of the photon emissions to just optical fibers connecting Alice and Bob, you can do far better in terms of the scaling and the actual rates. If you decide to do time multiplexing, meaning here if you wait for some little m number of time steps and you keep generating entangled states, and then you decide to mix and match successful entangled states generation over a block of time modes, then you can get an entanglement rate that goes sub-exponentially with the distance of the fiber. You can go e to the minus square root of alpha L instead of e to the minus alpha L. And there's a lot more work in quantum repeaters that brings in entanglement distillation that I will not talk about. But this repeater architecture design itself is an extremely challenging and extremely interesting task. We are working with Professor Ido Vax, Norbert Linke at University of Maryland to design quantum repeaters built with trapped ion qubits. So trapped ions is another candidate for building quantum memories. They are longer lived. They don't require dilution fridge-like temperatures like these hundreds of millikelvins that our color center qubits need. But they're potentially not as scalable. But you can do very good quality quantum logic on collections of trapped ion qubits. So doing those distillation codes, these are perfect candidates. So that's what we are exploring with these trapped ion quantum repeaters. You can build all photonic quantum repeaters. I talked about cluster states. You can mimic the action of a quantum memory by an entangled state of many photons that stay locally within a repeater where one photon entangled with that cluster state flies to the middle of the elementary link to that Bell measurement. And even though all these photons in this entangled state are going through loss locally, a quantum error correction code that cluster state represents that protects that logical qubit that you're holding on to against optical loss seen as the quantum error mechanism. So this is a very interesting idea where you don't ever have to go back and forth between spin quantum memories and photonic quantum memories. Something that we are not pursuing as part of CQN, but work being done in collaboration with Lin Ran Fan as part of an Oak Ridge National Lab DOE program. You can generate photonic cluster states also using these same color center emitters. You just have to keep going. You just don't stop at that two photons. If you remember that microwave and laser excitation, if I kept going, you can generate 3 photon, 4 photon cluster states. So you can use the same spin memories to generate cluster states. And this is just a cartoon from a paper I did a few years ago that showed that if I had 3 photon cluster states as a starting resource, even with probabilistic Bell measurements in the optical domain, you can build an all photonic quantum computer where you generate a large spanning photonic domain cluster state with probability almost 1 using tools from percolation theory. So this form of quantum computing is now being pursued by a company called Saiquantum. They are based in Palo Alto. They are building quantum computers using photonic qubits. Talking of photonic qubits, I talked about the dual rail encoding. That's not the only way you can encode a qubit in a photon. A qubit is an abstract concept, like a bit is a 0 or a 1. You can encode it in different ways in light, right? BPSK, QPSK modulation. A bit can be encoded in a magnetic storage. Qubit, there are many ways in which you can encode it in the photons. You can ask the fundamental question of all the different ways you can encode a 2-level system in a bosonic mode. What is the one that is the most resilient to loss in propagation, for example? That itself is a very hard question. My colleague Liang Jiang, his group has been working on this problem for the last several years, and he's found this thing called the GKP qubit. I won't have time to go to the mathematics of this. Gottesman, Kitaev, Preskel qubits. They are the most resilient to lossy propagation, and hence they are a very good candidate for quantum repeaters. And no surprise, this is unpublished work still. We are seeing about 2 orders of magnitude improvement in the number of photon sources that you need for building all photonic repeaters if you use this GKP encoding. There is a whole bunch of research we are doing, collaboration with Lin Ran, Christos, and our students on how do you generate GKP qubits and cluster states built out of them. Again, I won't have time to go into this. So let me spend the last few minutes that I have to talk about networks. Okay, this is the where it all comes together. So I talked about so far, just a recap, sending qubits, the 2 ways in which you can do it, by teleportation or by direct communication with error correction. But the end product of all of that I was talking about is still this one elementary link, an entangled state between 2 parties. So how do you take it forward to multiple parties and support many applications simultaneously on a network? So what is there in a node in a quantum network? So I mentioned a few things. There's quantum memories that can hold on to a qubit. You need an interface to photons, because photons are the kind of qubit that can fly. So you need that interface to loading photon or generating photons entangled with memories. You need to be able to do measurements on collections of qubits, 2 to 3 qubits, for example. You need to be able to do some gates, like those microwave spin control I was talking about on the qubits. You need some classical communications and computing interface, and maybe even photonic entanglement sources. Now, not all of these things will be inside a quantum network node. But simple questions that you can start asking, and even though the problems are such simply stated, they very quickly become very, very hard to answer. So it's a very, very simple problem here. Quantum network in a square topology, Alice and Bob. Every network edge is generating a Bell state with probability P. P is proportional to the transmissivity of that link, just like I mentioned. So that all of that has been done in the physical layer. You're now at the network layer. I'm sitting at a repeater over here. I know where Alice and Bob are. At any given time step, I know which of my neighboring edges of the network successfully generated a Bell state. And my job is to decide which 2 qubits should I make a Bell measurement on, okay, in order to maximize the entanglement rate between Alice and Bob. And turns out that even using what is called a local link state knowledge, this is where terminology borrowed from classical networking. So there are people like, say, Don Tousley, he's a renowned computer network theorist, did a lot of the early work on IP and TCP that are underlying our classical networking protocol stack. Using just local link state knowledge-based routing, you can outperform quantum communications over the shortest path connecting Alice and Bob. Now, once you allow, you can ask, well, why do I even do a Bell measurement here? Why cannot I do a measurement on 3 qubits together? What is so special about a Bell measurement? If I have entanglement to 3 parties, and I'm sitting here, if I do a 3-qubit GHZ projection, a projection onto one of the 8 orthogonal states of 3 qubits, just like there are 4 orthogonal Bell states, there are 8 orthogonal GHZ states. So I can do a projective measurement on 3 qubits. So the moment I allow for 3-qubit or multi-qubit projective measurements, what happens is that you can be in a regime of probability of success of every link and probability of success of making that GHZ projection, such that your end-to-end entanglement rate does not depend upon the distance anymore. So forget this exponential decay. You can do much better than that. If you allow for time multiplexing, meaning you hold on to these entangled states over, let's say in this case I'm showing 3 time steps or 3 time blocks, and then choose what collections of GHZ projections to make on collections of qubits, then you can push that percolation boundary of P and Q to further out and have this distance independent rate feature over a more robustly. Now here I'm not even talking about entanglement distillation. So this is all at the link layer, below. So the physical layer takes care of the error correction, generating that link in the probabilistic fashion, a heralded fashion, and then you're doing these things above that layer. Then you can ask questions like, you have 2 parties. So Alice 1 and Bob 1 running one session, Alice 2 and Bob 2, the green nodes are running another session. If there are 2 users in the network, there is a certain region of repeaters that are the most useful to them. So if those useful regions of the repeaters intersect, what should the repeaters in the middle do? Should they time share between serving this flow and that flow, or should they do something more clever? And turns out that you can do something better than just simple time sharing between multiple flows. You have, let's say you have to generate both bipartite and tripartite entanglement. Perhaps in the future of the quantum network, there's 3 sensors, like say 3 telescopes trying to generate GHZ states to improve their performance. And there are 2 users who are wanting to generate just Bell states to do an Eckert 91 key generation protocol. How do you support both of these 2 at the same time? Well, should the network be time sharing between generating this bipartite and tripartite entanglement? And turns out, no, there are better ways to do that. You can outperform this time sharing between optimal protocols. Even this work was done by Gayane Vardoan, former student of Dawn Tousley. She's just accepted a faculty offer at TU Delft, which is a center like ours in CQ and led by Stephanie Wiener in Netherlands, and they are doing a lot of work in quantum networking. Even this simple problem turned out to be a really long tour de force with in Markovian dynamics and analysis that it was extremely hard to solve. So the moment you make these problems complex, the solutions become extremely hard. Similarly, we looked at this problem of, again, Prajit in collaboration with Don's student Nitish Panigrahi, developed a mixed integer program to optimize the placement and the assignments of sessions to a network of satellites to maximize some weighted sum of rates that is supplied of entanglement between different pairs of ground stations. And for certain cases, you can solve these things. For certain cases, it becomes extremely hard. In CQN, we are looking at stability analysis of queues, generalizing the concept of max weight scheduling. Leandros Tasiulas on our team from Yale University, his claim to fame is what is called back pressure routing that came from wireless networking. It's a kind of routing algorithm that is throughput optimal when you are in a high congestion regime. So there are ideas from that are being transported into quantum networking. So there's a whole host of problems on resource allocation, network control, tomography, network design, and developing that whole network protocol stack. I only talked about the physical layer in a little bit detail, but the whole network protocol stack, I'm not talking about that in detail, but there's a lot of work in that computer science domain. So we went from material science to physics, from photonic engineering to the error correction theory, now to computer networking, and then the application layer. It's a center that spans people who don't even speak the same language. I mean, it's a huge undertaking. Dirk England's group at MIT, working with several other people in the Boston area, they're leading a testbed in the Boston area. It's a fiber-based testbed that connects MIT Lincoln Lab in Lexington, Massachusetts, to MIT main campus in Cambridge through a 43-kilometer-long dispersion-compensated optical fiber. From MIT, you go to Harvard University, and Harvard to BBN Technologies. This is a company I worked at for 9 years. So the experiment that I talked about on that asynchronous Bell basis measurement to beat the repeaterless bound, hopefully in the next few months we'll see a paper come out of this where we will demonstrate this experiment on this testbed. Zheshen Zhang at University of Arizona, he's recently left for University of Michigan. Now Lin Ran is leading the testbed at University of Arizona. We have a campus fiber network. There's one free space link. This connects 10 laboratory sites across 6 buildings on campus. We have entanglement sources, we have fiber switches, superconducting nanowire single photon detectors, all as a shared resource. If you want to do some experiment with detectors in some other lab, there's a source in some other lab, you can just query that over the network. So this was all Zheshen built it all up. We are working on building our quantum memory capabilities that will be included in this network very soon. So I already talked about quantum entanglement assisted sensing. There is a very interesting thread of work we are doing on quantum limits of passive imaging, collaboration with Amit Ashok's group in OSC. And I won't have time to go into the detail of this work, but long story short, if you have, say, a constellation of stars or fluorophores that you're imaging that are highly tightly sub-Rayleigh, meaning their angular separations are much smaller than lambda over d. Lambda is the wavelength of light, d is the diameter of your telescope's pupil. If you precede your detection with a spatial mode sorter, a multi-spatial mode transformation device that can be adaptive, meaning what modes you sort is adapted based on the actual dynamically detected photon events. You can resolve these point emitters that are direct imaging focal plane array. Even the best possible ones cannot. So CQN is just divided up into 3 thrusts. I don't see Jane here. I think she's a professor of law, University of Arizona. She is leading a very unique thrust called Thrust 4, which is researching societal impacts of quantum technologies. And this is a thrust made up of researchers from background in laws, social behavioral sciences, economics, and so forth. They're looking at problems like inequality in access, equity related issues in the applications that might come out of this, and unintended consequences of quantum technologies. Lots of very interesting questions there. So list of CQN senior personnel. We have Stephen Fleming sitting over there. He's our a yellow officer. He leads our industry partnerships. And Stephen has been very successful in getting a huge industry support. This is a growing list. There's one missing. Okay, I cannot keep up with you. And these are companies that his top level members, they're called diamond members. They pay a pretty sizable membership fee, $150,000 a year to be members of CQN. And they get to do research with the students here. If you're interested in learning more about it, talk to Stephen. We have a MURI program looking at the theoretical aspects of complex entanglement. Julie Ems is sitting over here. She's our administrative director. She, with help of many faculty members here, and Brian Anderson launched a master's sub-plan within the optical sciences master's program. So those of you here are interested, it's open for enrollment. It's already, I think we have 35 students enrolled already. So the program is online. We'll be working on it. We all know the construction happening in our backyard. So CQN will be on the 4th floor. All of 4th floor was custom designed by our faculty members, postdocs. The third, Matt Eichenfeld will have a big superconducting qubit lab on the 3rd floor that will be connected to the 4th floor as well. You know, one of the fewest things that is happily bipartisan these days is Quantum Information Initiative. So we have, so the NQI was signed a few years ago, and this is an old number that is closer to $2 billion that the government has put in the last, just during COVID alone. During COVID, there were 12 centers that were funded across the US. So 6 by the Department of Energy, so 5 NQI centers and 1 center focused on quantum networking. And NSF funded 5 centers out of their NQI budget, and our ERC, which was not part of the NQI budget. ERC is an old program running from 1985, so it was funded out of NSF's line item budget out of ERC. So very good time to be working on this field, but you know, and there's lots and lots of challenges across the span of disciplines that I talked about. But of course, we have to stay up on our game. So there's a timing seems good, but time will tell if the community lives up to the high expectations. We need to find more applications. We need buy-in. We need technology maturation. We need stakeholder identification and adoption of the technologies. Right. So with that, I'll thank all my students, my group members, and the funding agencies, and take any questions if there are any.